Hey everyone, welcome back to Edgeverse. Or if you're new here, buckle up because today we're diving into one of the coolest, mind-bending ideas in modern science. Imagine the universe has a hidden language, not made of words, not made of light, but made of pure gravity. A language written in ripples of space-time itself. And for the first time in human history, we are learning to read it. That's what gravitational waves are. The universe whispering, shouting, and sometimes screaming its deepest secrets directly to us. No dust clouds blocking the view. No atmosphere scattering the signal. Just pure, pristine information from the most violent events in the cosmos. Today I'm going to take you on a 20-minute ride from Einstein's century-old prediction to the latest discoveries, and even into the future, where we might finally hear the echo of the Big Bang itself. Let's go. Chapter 1 in our story starts over 100 years ago. 1915. Albert Einstein finishes general relativity, the theory that says gravity isn't a force, it's the curving of space-time by mass and energy. A year later, he realizes something wild. If something massive accelerates unevenly, it should send out ripples in space-time that travel at the speed of light. Gravitational waves. But Einstein wasn't even sure they were real. The math said yes. His intuition sometimes said maybe not. The ripples were predicted to be absurdly tiny, stretching a 4-kilometer detector by less than the width of a proton. Detecting them seemed impossible. Fast forward to 1974. Two astronomers, Hulse and Taylor, discover a pair of neutron stars orbiting each other and losing energy exactly the way Einstein said they would if gravitational waves were carrying it away. They won the Nobel for that. Indirect proof. Beautiful, but still no direct detection. Then, September 14th, 2015. Two black holes, each about 30 times the mass of the Sunday, January 3rd billion light-years away, spiral together and merge. In the final fraction of a second, they convert three solar masses into pure gravitational waves, more power than all the stars in the observable universe combined for that brief moment. And two LIGO detectors, one in Louisiana, one in Washington State, hear it. A perfect rising chirp that matches Einstein's equations to exquisite precision. Humanity had just opened a brand new set of ears. We were no longer only looking at the universe. We were listening to it. So what exactly are we hearing? Every gravitational wave that reaches Earth is a message that contains precise information about what created it. Take that first detection, GW 150914. From a single 0.2-second chirp, scientists measured the masses of both black holes, their spins, how fast they were orbiting in the final moments, the mass and spin of the new, bigger black hole left behind, and the distance, 1.3 billion light-years. All of that, with no telescope, just two laser beams watching mirrors for the tiniest jiggle in space-time. It's like the universe handed us a postcard with the sender's full biography written on it. Every binary merger has three parts to its story: the long inspiral, a beautiful rising tone as the orbit shrinks; the violent merger, the loudest moment when horizons touch; the ringdown, the new black hole rings like a bell until it settles. Each phase tells us something different. The inspiral is amazing for measuring masses and spins. The ringdown confirms the no-hair theorem. Black holes are completely described by just mass and spin. If the ringdown ever sounds wrong, we might have discovered exotic objects or new physics. And then there's the 2017 neutron-star collision, GW 170817. That one was special because it lit up across the electromagnetic spectrum: gamma rays, X-rays, visible light, radio. We saw the exact moment short gamma ray bursts are born. We watched the universe forge gold and platinum in real time through the R process. And we measured the speed of gravity to 1 part in a quadrillion. It's exactly the speed of light, just like Einstein said. Multi-messenger astronomy was born. But mergers aren't the only speakers in this cosmic language. There are continuous waves. Think rapidly spinning neutron stars with tiny mountain ranges on their surface, broadcasting a steady gravitational hum. There's the stochastic background, a faint hiss made of thousands of overlapping mergers across cosmic time, plus maybe echoes from the early universe. And then, the Holy Grail, primordial gravitational waves from the Big Bang itself. During inflation, That insane period when the universe expanded faster than light for a tiny fraction of a second, quantum fluctuations got stretched across the cosmos. Some of those fluctuations were tensor modes, baby gravitational waves. If we ever detect those, we're looking back to 10 to the minus 36 seconds after the Big Bang, before light, before atoms, before anything we've ever seen. The main way we're hunting them right now is through B-mode polarization in the cosmic microwave background. We haven't found them yet, but every new limit tells us something about the energy scale of inflation. Future space detectors like LISA, Big Bang Observer, or DESIGO might hear them directly. Imagine hearing the universe when it was smaller than a proton. That's not science fiction. That's the 2040s, maybe sooner. There's something called the gravitational wave memory effect, a profound phenomenon that permanently alters the fabric of spacetime. Unlike normal waves that pass and leave no trace, some gravitational waves leave a permanent scar on the very structure of the universe. After a massive cosmic event, like the merger of two black holes, the fabric of the universe is very slightly, yet permanently, stretched in one direction and squished in the other. It's an incredibly tiny effect, far below the sensitivity of our current detectors, but its significance is immense because it never truly goes away. Space-time remembers, accumulating a cosmic ledger of the universe's most violent moments. Over billions of years, every explosion, every merger of colossal objects, adds a little bit to this memory field, written directly into the geometry of the cosmos. The universe is quietly accumulating a permanent record of its most energetic events, a silent history etched into its very foundation. That concept alone is truly mind-blowing, fundamentally changing how we perceive the universe's past and its ongoing evolution. So, where does all this leave us in our quest to understand the cosmos? We used to think the universe was mostly dark, with 95% composed of dark matter and dark energy that we can't see with light. Gravitational waves, however, don't care about these obscurities. They sail right through everything, offering a pristine view. They're already helping us in incredible ways, revealing secrets light could never uncover. For instance, gravitational waves are mapping dark matter substructure through gravitational wave lensing, providing unprecedented detail. They're also measuring the expansion of the universe with standard sirens, a method that requires no complex distance ladder. Furthermore, we're using them to search for new particles like axions that form clouds around spinning black holes and emit continuous waves. And if quantum gravity is real, if space-time is foamy or discrete at the Planck scale, high-frequency gravitational waves might show dispersion or echoes around black holes. We're building detectors for that too, pushing the boundaries of what's observable. The next 20 years are going to be absolutely insane for gravitational wave astronomy, promising a revolution in our understanding. Third-generation ground detectors, like the Einstein Telescope and Cosmic Explorer, will see every stellar mass black hole merger in the observable universe. LISA, our space-based observatory, will hear supermassive black hole mergers from the very dawn of galaxies, peering back into cosmic history. Pulsar timing arrays are on the verge of confirming a nanohertz background, opening a new window into the universe's lowest frequencies. And artificial intelligence is going to be our translator, sifting through millions of signals, finding patterns we can't even imagine yet. We're moving from simply asking, "Can we hear gravitational waves?" to the much deeper question, "What is the universe trying to tell us?" So here's the big picture I want you to leave with, a perspective that reshapes our cosmic understanding. Everything we've ever seen with light is just one channel, a noisy, dusty, absorbed, and scattered channel. Gravitational waves are a second, cleaner channel, and it's been playing the whole time, for 13.8 billion years. They carry information from places and times light can never reach, offering an unfiltered view of the universe's most ancient and extreme events. We're the first creatures in the universe, that we know of, who have built ears sensitive enough to truly listen to this cosmic symphony. And the universe, with its gravitational whispers and roars, has a lot to say. If this video blew your mind even a little bit, do me a favor, hit that like button, subscribe, turn on notifications. Drop a comment. What gravitational wave discovery are you most excited for? Primordial waves? Memory? Something else? I read every single comment. And if you want to go deeper, I've put some incredible papers and resources in the description below. Thanks for spending the last few minutes exploring the cosmos with me. Until next time, keep looking up and listening.